Hi everyone, I am Balaji Chippada and welcome back to my YouTube channel. In continuation of our series Probability and Statistics, in this video, let's learn about symmetric distribution and then skewness in the distributions and one more important factor called kurtosis. You will learn all of these three things in detail and their intuition. So without any delay, let's get started. In the previous videos, we have learned about normal distribution, right? Which is like bell-shaped curve, and we have something like this. So this is called PDF function or probability density function. And then we have learned about CDF as well, right? CDF is something, if you remember, we have something like this, and it is of 0 and 0 to 1, which values between 0 to 1, cumulative values, right? We have learned about PDF and CDF, and we have learned about these things. Now let's understand symmetry in detail. If we have a distribution like this, and then it is centered at my mean value, so let's assume this is my mean mu, or you can call it as x bar as well. So let's assume it is a value 0. So what we learned in terms of a symmetric symmetric distribution, we see that approximately, not approximately, 50% of your point lies on the right side of your mean, and then 50% of your point lies on the left side of your mean, and then we have the same kind of decline from either side of the mean. So we have, if you look at this slope and this one, it is very similar, it's almost same. And if you calculate length at any point, let's take like this. So this is the meeting point, this is the meeting point, this length is equal to this length at any point of the curve. So this is what we call it as a symmetric distribution. Now you might ask, are there any other distributions? Yes. So let's say I have a distribution like this, and I have one more distribution like this, and here we have some value x0. Let's assume it might not be the mean, because in terms of unsymmetric distributions, these are unsymmetric or asymmetric distributions, your mean might not be at the peak value. So this is some point, and even if you draw any line at this graph, there is no way it is going to be same on the either side of the line. So these are called unsymmetric distributions, and we also call them as skewness in the distribution. We will learn about skewness in detail as well, but for now let's learn everything regarding symmetric for now. So to understand this symmetric distribution mathematically, so I have searched for symmetric distribution Wikipedia. As you have already know, most of the things I learn from Wikipedia, it is a great source to knowledge actually. So if you look at this, so this is my distribution which is symmetric, and let me explain this. So what they are saying is f of x naught minus delta is equal to f of x naught plus delta. If any distribution follows this formula, that means they are symmetric in nature. So let's explain or understand what this is in detail from this plot here. So let's take x naught as a mean, okay, and then we have delta is any value. So what they are saying, x naught minus delta, so let's take delta as 2 units. So from 2 units mean, this is the point, and from 2 units on the right side, this is the point. So what they are saying is, if I do this like this, these two should be on the same height. So this function curve is called f, and this is my x on the x-axis. So what is f of x? F of x is the height at any given point. So what we are saying, f of x minus delta equal to f of x plus delta. So what does mean? From any given point from the mean, it should be on the same height. And if that satisfies, then the distribution that we have is called a symmetric distribution. If you can take any other point, like let's take these 2 points, the height is going to be the same, given that these two are on the same distance from my mean value. So if that follows this equation, then that distribution is called a symmetric distribution. Hopefully that is clear. Now let's learn about skewness. So let's go to Wikipedia again and type in skewness, and then you will get to see this one. If you see here, I have two plots which is positive skewed and negative skewed. So what is a positive skew and what is a negative skew? So let's learn about that. If I draw any line anywhere, I am not going to get my graph in a symmetric fashion. So that is what we call it as a skewness. What is a left skew and what is a right skewed? So this is called a left skewed and this is called right skewed. Why it is called left skewed? If you look at this slope, it is going and going and going towards left side, and if you see this distribution, it is going towards right side. So that is why it is called left skewed and right skewed, and we also call it as a negative skew and a positive skew. So these are all the different kinds of names that we give for the skewness of the distribution. Hopefully that is clear. Now there might be so many data sets in the real world which will follow this skewness, because not everything in the real world follows a normal distribution. You will have the right skewed data, you have some skewness of the data in the real world as well. And in real world, most of the times when we are working in the real time data sets, I hardly see any data with a normal distribution. We mostly deal with the skewed data. Either it could be negative skew or a positive skew. Hopefully that is clear. And we have a mathematical equation actually to calculate the skewness. So let me explain this. So this is the formula. Where is this? Okay, this is the formula uh, to calculate the skewness actually. So if you look at this carefully, this is looking like a variance formula, right? This is not exactly variance, but it is similar to variance because we have a power 3. In case of variance, we have a power 2. So what is this x bar? X bar is the mean. So if I have points x1, x2 up until xn, what is my mean? Sigma xi, I equal to 1 to n by total number of elements n. So this is called x bar. First I have to calculate my mean and then subtract this from my mean from every element and then cube that power and then sum it up and calculate by n, which is called variance. Similar to variance, not exactly variance. And here we have similar to standard deviation, but because if you we have 3 by 2, let's say I have a power 3 by 2, so this I can write it as square root of a cube, right? So it is basically square root of my approximate variance. So what is square root of variance? It is standard deviation, right? So this formula is very simple, which is basically variance by standard deviation. But while calculating these two things, instead of power 2 we are using a power 3, and in denominator we are using n minus 1. Hopefully that is clear. So this is called the skewness of a distribution. This could be any value, let's say 50 or maybe 60 or 70. It could be any value actually. And why are we needing these values? So let's say I have two data sets. So I will take this. So I have something like this and I have something like this. So both of them are right skewed, but one is more right skewed compared to the other one, right? Clear? But how much right skewed difference between these two plots? If you want to calculate, then you have to calculate using this formula, and then let's assume you have a right skewed of 50 value. Here, because this is more right skewed, you will get a value of 80. Because this value is bigger compared to this value, my distribution for this dataset D2 is having more right skewed compared to my distribution D1. So this is why we need to understand. In real life, how will you visualize this? So let's say some person came to me and said that I have a dataset D which is of 10,000 points and it is of right skewed. Then in my mind, without even looking at the data, I can think of something like this because it is of right skewed. So you will get to understand the distribution of data or the PDF of data even looking at the data by knowing what kind of skewness the data is. Hopefully that is clear. And then we have something called as this one, positive skew, negative skew, and mean normal one, which is basically this is very important actually. Let me explain. So if you look at this one, we have a positive skew plot, symmetrical distribution, and a negative skew plot. These are the three possible things, right? So in terms of a symmetrical distribution, your mean value, median value, and mode value are same. In terms of a positive skew distribution, your mode less than median less than mean. This is an interview question actually. So how do you get to know what kind of distribution or skewness your data has, given that you have mean, median, and mode? If someone give me mean, median, and mode, by looking at these values, I can concretely say that whether my data belongs to positive skew or a symmetrical distribution or negative skew. In terms of negative skew, my mean is less than median, less than mode. So these are the two rules that you can bring up in terms of skewness of a data. This is an important interview question, and most of the times you can expect this to be asked in the interviews actually. So let me rephrase once again. In terms of positive skew, you have mode less than median less than mean. In terms of negative skew, you have mean less than median less than mode. In terms of symmetrical distribution, we have mean equal to median equal to mode. Hopefully that is clear. Now let's learn about kurtosis. So we are back on Wikipedia again. We searched for kurtosis Wikipedia and we got this page. By now you might have observed that most of the things that I learn are mostly from Wikipedia. Although I do read research papers and all that stuff, but mostly for general knowledge and getting to know what things are, Wikipedia is more than good enough. Now, what is kurtosis? Kurtosis is basically a measure of tailness of a distribution. So you might raise a question, right? Then what is skewness? Skewness is also similar to kurtosis. In skewness also, we will learn or calculate the tailness of the distribution. So this is called tailness. Tailness. So whether it is leaning towards left or whether it is leaning towards right, and how much it is leaning, even that we will understand via skewness. And mostly skewness you will understand about right or left. Kurtosis is also a measure of tailness, but it will help you understand with respect to a normal distribution how your distribution is varying. Given the value of kurtosis, I can definitely assume what my data set looks like. So we'll learn about that in a bit. So let me show you the formula of kurtosis. It might be a little bit complex, but let's not worry. No one is going to ask you in the interview regarding the formula of kurtosis. But if you look at it, this is the formula for kurtosis. It is similar to what we have seen in the skewness, but here notice we have power 4 and square power square. So it is basically similar to variance, but not exactly variance. And then here we have the standard deviation, something like that. But we have something called as -3. So why this -3? Let me explain that in a bit, so don't worry. But here if you look at it, this is called an excess kurtosis. Excess kurtosis. I will explain what this excess kurtosis is and how it is different from kurtosis in a given minute, so don't worry. So this is basically an excess kurtosis. Give anyone, if they give me a value of excess kurtosis, I will be able to understand how the distribution plot or PDF will look like actually. So how am I going to conclude that? So we have a nice plot here. Before understanding the plot, you can check the example values that are provided here. You have a lot of values, and then you have an outlier as well, 999, and they have calculated the kurtosis value actually, which is 15.05. So based upon this, you can understand the calculation part as well. But I want to explain this here. If you look at it, this is an excess kurtosis plot in which this is a Gaussian distribution. So let's say I have a random variable x which follows a normal distribution, and if it is a normal distribution, its kurtosis value is equal to 3. So if my kurtosis value is 3, what is my excess kurtosis value? Kurtosis value minus 3. We have seen that, right? Let me show you that again. So if you look at the formula, this part is called kurtosis, and you are subtracting minus 3, and the whole thing is called excess kurtosis. Clear? So given a random variable x which follows a normal distribution and its kurtosis value is 3, then the excess kurtosis value is going to be 0, right? Because 3 minus 3 is 0. So that is why we have this Gaussian distribution, and it is having excess kurtosis value 0. If you look at this orange plot, which is this one, which is 3, what is this 3? This 3 is called excess kurtosis value, and if my excess kurtosis value is 3, my kurtosis value is 6, and with comparison of the Gaussian distribution, it is much more in terms of height, and there is no smoothing on the top. It is a peak value, and then it is drastically reducing with compared to my Gaussian distribution, right? All of this is getting changed because I know that my excess kurtosis value is 3. So by given the excess kurtosis value is 3, I will get to know that this is how my distribution would look like. So you have another one which is excess kurtosis is 2. So the kurtosis value is basically 5 because we are subtracting 3 from it. And this is how my distribution would look like with respect to my Gaussian distribution. It is of more height and it is reducing more fast actually. So this is called tailedness, right? Tailedness. And let's not confuse about whether excess kurtosis is dealing about the peakedness. It is not talking about peakness. Initially people thought excess kurtosis is talking about the peakness of the curve, but it is not the case. After a lot of research, excess kurtosis is mostly the measure of tailedness, how fast the curve is declining with respect to a Gaussian distribution. So by looking at the excess kurtosis value, I can quickly assume what is the structure or PDF of my given plot. If you see, I have a Laplace distribution. This is not a normal distribution. If my data follows a Laplace distribution, then my PDF will look something like this. If my data follows hyperbolic secant distribution, my data PDF will look something like this. So you don't need to learn about all of these distributions. Of course, we will learn about something like log normal distribution, box clocks. There are a lot of things that we will learn, but not everything. But what you need to grasp is by looking at the kurtosis value, I will be able to understand the peakness and tailness of a given data set without even looking at the data. So this is what kurtosis means. Hopefully that is clear. And that's all for this video, guys. We have learned about what is symmetric distribution, what is skewness, left skew, right skew, and mean median mode in terms of skewness, and what is kurtosis and how it is different from the skewness, and how you can expect the PDF would look like given the excess kurtosis value. If you have any queries so far, please let me know in the comment section below. And if you are enjoying what you are watching, and if you are learning something new, a sub to the channel would be amazing, and click that bell icon to get notified daily. We'll meet in the next video. Bye bye.